just look at a periodic table and figure out what charge they'll have or why they behave the way they do. It's not as obvious. Now, what we're going to do now is assign names to the families. There's only 4 that you need to know. It's kind of like their last name in a way. You can think of it like that. So, the first group is called the alkali metals, right here. Those are the group 1 metals. So, they happen to be the first column, they're called group 1 metals. Now, one of the things you'll notice is, who's left out in the first group?
Hydrogen.
Hydrogen.
Non-metal.
Hydrogen, yeah, is considered a non-metal, so it's not going to fall into the alkali metals, right? Now, there's a reason why it's there, and we'll learn about that when we start talking about electrons and protons. Second family is the alkaline earth metals. So you have group 1 metals, group 2 metals. Then you have the transition metals. It's all one category here. In between the transition metals, you have the lanthanides and the actinides. So this whole thing, they're called the lanthanides. It's just because here, the first element happens to be lanthanide. And then here, these are called the actinides. And that's, again, because number 89, where it branches off, is the first element. Now, these two, one of the reasons why they're actually branched off is more for practical reasons, in the sense that a lot of these are man-made. You're not going to use them or see them on a day-to-day basis, especially in compounds. Most famous one would be like uranium, and that's it. And another thing is, if we were to stick this whole thing in here, it's going to cause the periodic table to be really long. Are you going to be able to fit it onto an 8 by 11 paper? Most likely no. You have to shrink it down. So it's not practical. It's not able to fit on a piece of paper as well. That's the other reason. And then if you look on this side, there's only 2 families you need to know. The halogens, which is group 7, and then the noble gases, which is group 8. Now, how I got that number, 7 and 8, is because I'm just looking at main group elements. 1, 2, 3, 4, 5, 6, 7, 8. I'm skipping the transition metals, because the transition metals are not as predictable. Main group elements are much more predictable. Now notice the only 4 families that you had to name were 2 of them on this side at the edge and 2 of them on this side on this end. That's because these are the most reactive families that you'll encounter. You do have other families here, but they're not as reactive. These are much more reactive, and you'll learn about their properties when we get into electrons and compounds. So you'll see them. And you'll notice they have very similar charges to each other. Okay. So remember, an atom, it's neutral, has no charge to it. Number of protons equals the number of electrons. Anytime I say ion, it's going to have a charge to it, because the number won't be equal to each other. Now, it just depends if it's going to have a positive charge or a negative charge. You won't know that till you compare the protons and electrons. So ion is a charged entity. It can either would gain or lose electrons. Now notice I only said electrons. Because if you change the number of protons, what are you changing?
The identity.
The identity of the element. I'm not saying to change the identity of the element. I'm just saying you're changing the electrons, that's it. Now, example of this would be something like this. Here, I have magnesium, the atom. Notice there's no other positive or negative charge surrounding it. I just put Mg. Now, if I do this, now that's an ion. Because notice it has a number and it's telling you it's positive. So here, there's something going on that's causing it to have a net charge of positive 2. Now, who's bringing the positive aspect?
The protons.
The protons, right? The protons are bringing that positive charge. So this is telling you that here you have a neutral magnesium atom. Notice it says 12 plus here, meaning 12 protons, has 12 electrons. Now, when it loses 2 electrons, right, this will stay the same, because you're still talking about magnesium. You can't change that. But notice your number of electrons drops down to 10. So, in order to show that, you want to compare the number of protons and electrons. You have 2 more protons than electrons. 2 more protons, which are positively charged, than electrons. In order to do that, you have to lose 2 electrons. So the biggest thing to understand is know your charges and understand what this means. You have 2 more protons than electrons. In order to get that, you have to lose 2 electrons. You cannot lose protons because then you're changing the identity of that particular ion. Another name for this, instead of saying ion or a positive ion, it's called a cation. That's a positively charged ion. So positively charged ion. That's called a cation. A way to remember this, a cat purrs, cation, positive, right? A cat purrs. This is just if you have like a mathematical kind of mind to it. If you're trying to figure it out, you can set it up as a math problem and see that, okay, here you have 3 protons, and then here you have 2 electrons, which are negatively charged, positively charged, right? You can subtract the 2 to figure out the charge of that electron, or that ion. So you can set it up as a mathematical equation. So here, as a positive charge, what if we do the opposite? Negative charge. So here we're looking at chlorine. Chlorine is element number 17. 17 protons, 17 electrons. This is the atom. Now, we're saying it's going to add 1 electron. This will not change, but notice now you're going to 18 electrons. It gains 1 electron. Now, when I compare the two, I have 1 more electron than proton. Because of that, it's going to be negatively charged, because you have 1 more negative particle than a positive one. These electrons are negatively charged. This, when we look at this, this is called an anion. Now, when we actually talk about anions, the name changes also. let me show you this. Here, notice the name. They just said it's a neutral magnesium atom. Here is magnesium ion, right? Magnesium stayed the same. Spelling didn't change, nothing changed about it. When we look at anions, the name changes, the suffix changes. Here you have chlorine atom. Now you have chloride ion. The INE changes to IDE. So you add a suffix, you change that. And you can do that with a lot of the non-metals, because they tend to gain electrons. So instead of saying oxygen, you'll hear oxide. Fluorine, you'll hear fluoride. Bromine, bromide, IDE. You see that a lot in compounds. You'll see that IDE. And we'll get into that when we talk about nomenclature, naming compounds. Now, whenever we're doing these charges, one thing that you have to keep in mind, if it's just gaining or losing one electron, we don't put a 1 here. So notice I don't have a 1 here or a 1 here. We just assume that it's 1 electron that's being gained or lost. If you're losing 2 or more, you have to indicate that number. Now notice the number always comes first, then the charge. So don't write here, don't write it like this. Not +2, it's 2 plus. It has a particular order to it. So always the number first, then the charge. And then if you gain or lose 1, you just indicate the charge, not the amount, because it's already assumed it's going to be 1. And you can see that example here. This is dealing with fluorine that turns into fluoride, IDE. Now, one of the things that you'll notice when you compare the families, they are genetically related. They behave very similar to each other. So, they form the same types of ions. Notice the alkali metals right here all have a +1. Alkaline earth metals all have a +2. Group 1 metals always lose 1. Group 2 metals always lose 2 electrons. Group 3, there's only 3 of them here. They're going to lose 3. And then when you get onto this side, one of the things you'll notice is they start gaining electrons instead. And this side of the periodic table is classified as what type of metal? Non-metals. So the non-metals do like to gain electrons. Here they're gaining all 2 electrons, and then here they're gaining 1 electron. One of the things you'll notice is group 8, which are called the noble gases, don't like to do either. Noble gases think of royalty, right? They're automatically born into it. Do they have to work for it? No, right? But everyone wants to be like them, right? They're nobility. So think of the noble gases like that. They're unreactive, but everyone is trying to be like them. And you'll see that when we get into electron configuration, why these like to gain 2, these like to gain 1, why those are losing. We'll learn about why they want to do that. And then transition metals, right, form various charges. They're unpredictable. They can form either lose 2 or lose 3 electrons, even lose 5 electrons. So they vary in that sense. There's no pattern to it. If I look at sodium, right, any compound that has sodium in it will always have that charge to it. So So that's where that consistency is. It's not gonna change. I can look at sodium chloride, which is table salt, versus sodium chlorate, which is used in the dyeing process, or sodium bicarbonate, which is baking soda. So salt versus baking soda, both cases have sodium in it. You use it for different purposes, but if I look at the sodium, it's gonna have the same charge. So that consistency you'll see over and over again on these ones that are indicated. The ones that are missing, like these guys here and these, they're not predictable. So you're not able to do that. Now we're going to practice this. I have the lecture problems for chapter 4, where I give you a certain amount of information and you have to figure out the rest. Keeping in mind, periodic table is always provided to you. Let's see if you have to memorize it. Always do the periodic table.
I wonder if he's going to give us a card.
That's what I think.
Would you get number 5? Did you get an answer?
Number 5?
On his text, yeah. I didn't get an answer.
Yeah, I think so. I thought I was going to do so well on it though.
Me too. But the one where the fraction was to be at. Yeah, right? I don't know how to solve it.
I put it. At first I tried to put it into a decimal, but I
Yeah,
just
it was like
couldn't.
0.33.
Yeah.